Hello everybody, my name is Arsany, and in this presentation I'm going to introduce to you our paper FeGAN, Scaling Distributed GANs. This is a joint work with Rachid Guirguis and Anne-Marie Kermarrec from EPFL and Erwan Merrer from Inria. So, the system I present to you today is called FeGAN, and if you look up the Urban Dictionary for the meaning of FeGAN, you'll find this: a fake vegan who pretends to not want to kill animals and eat meat but secretly does. Yet, in our case, this is not quite true, because we acknowledge that this paper has some meat inside. Basically, we have another meaning for FeGAN. We divide FeGAN into two syllables, Fe, which stands for Federated Learning, and GAN, which is an acronym for Generative Adversarial Networks. So basically, this paper is about distributing GANs in the Federated Learning setup. Before digging into details, I'd like first to start with a quick refreshment on GANs and Federated Learning. Generative Adversarial Networks, or GANs, is a machine learning technique which goal is to generate data that looks like real data, in this example images, yet from random noise. To do so, GANs are composed of two neural networks. The first one is called the generator. This is the one that generates data at the end. Yet, to train this network, another network helps it, which is called the discriminator. Basically, this network takes some input data and then tells whether this data real or not. Using this output, both networks learn how to do their jobs better. The generator's job then is to try to produce better data that looks like real data to trick the discriminator. Both networks play this game together against each other until the Nash equilibrium is reached. In this case, the discriminator is always confused whether the input data is real or not, and at this point, the generator is ready to generate data from noise. Now let's move to a second big term in this presentation, which is federated learning. Federated learning, or in short FL, is a paradigm to train machine learning models on many devices that are potentially scattered over the globe. This paradigm consists in a central server that holds the ML model and a bunch of devices that hold their own local data. Each device keeps its own local data private without sharing it with other devices. Naturally, data on devices are not identically distributed, where the devices themselves have different hardware specifications. The training phase proceeds as follows. In each training iteration, the central server chooses some of the devices that are ready to contribute to training. Then it sends a model to these devices, which in turn run one training step using their own local dataset. After updating their models locally, the device sends their updates back to a server, which aggregates all these updates together and updates the global model too. But now the question is, why do we need to distribute GAN training anyway? First of all, data that can be used to train GANs is naturally distributed. Think of the amount of data generated every day on mobile phones across the globe. This data could be images taken by your camera or words that you type in any application. Second, training GANs is very time and resource consuming. For example, this article talks about a guy who wanted to train his own deepfake to generate videos, and it took him 2 weeks and around $550 to do so. For this, it seems that distributing such training on multiple devices is appealing. But why do we choose the FL paradigm? First, FL scales very well, actually much better than the other architectures. In this paper from last year, Google shows that up to 6K clients were trained by FL at a time. Usually, this number is at least one order of magnitude less with other architectures. Second, the design of FL keeps data private on devices, which is a desirable property in many cases. Finally, we believe that GAN-impressive applications that would be soon required to run on mobile devices, including image-to-image translation and creating new poses of photos. For all these reasons, we think that training GANs in the FL setup is really appealing. But one might think that this is trivial. It should be fairly straightforward to use some architecture to deploy GAN with. In fact, this is not true. First of all, the FL paradigm is designed to train vanilla ML models and was not designed to train GANs. For instance, a GAN is composed of two neural networks rather than one. What should be done with these networks? Should we put one on the server and the other on devices? And if yes, which network should be done where? And what are the trade-offs here? Second, GANs training is hard. Indeed, it might face novel problems that are not typical with training vanilla ML models. We highlight here two of these problems. The first one is called mode collapse. In this problem, the generator can generate data from only one class. For example, this instance in front of you in the slide, a GAN was trained to generate handwritten digits from 0 to 9. Yet after 100k steps, it can only generate the digit 6. The second problem we highlight here is called the vanishing gradients problem. This one happens when the gradient used to update the model is extremely small, to the point that the network cannot learn anything. In GANs, this happens when the discriminator is very powerful, to the point that it can detect all fake data that is generated by the generator. In this case, the generator cannot get any information from this feedback and fails to generate convincing data. Paying attention to these problems is extremely important, especially in the distributed environment. This brings me to introducing to you FeGAN, our system that enables training GANs in the FL paradigm while tolerating data skewness on devices and GAN-specific issues. The first decision we make is that we co-locate both networks, I mean here the generator and the discriminator, on all devices and also on the server. Having both of them on the same device allows training them together and hence reducing the probability of having a powerful discriminator and avoiding the vanishing gradients problem. The other two components that are extremely important in FeGAN design are the sampler and the aggregator, which both lie on the central server. The sampler is responsible for choosing devices to contribute to each FL round, where the aggregator is responsible for aggregating devices updates. The main goal of the design of these two components is to tolerate data skewness, which might lead to mode collapse and learning divergence. Note that for these two modules to work, we assume that nodes know the distribution of their data and that they share it with the server. Let's start with our first module, the sampler. FeGAN does what we call balanced sampling. In a nutshell, this technique tries to ensure the aggregation of a balanced number of samples per class in the updates applied on the model. This tolerates then data skewness and avoid mode collapse problem. Concretely, this happens by favoring devices with more samples, devices with balanced dataset, and unsampled devices in previous FL rounds. Let's for instance take this example. Imagine we have 4 devices and that the dataset contains 4 classes. These numbers at devices denote the number of samples per class the devices have. Assume that the server chooses 2 devices per round. In the first round, the server chooses the first and third devices. The first device has the most number of samples, and the third one has data from a class that was not seen before. It's not with the first device. In the second round, the server chooses the other 2 devices that were not chosen in the previous round. Our second important module in FeGAN is the aggregator. Basically, this aggregator applies weighted averaging to the devices updates, where such weights reflect the discrepancies between the local data distribution of devices and the global data distribution. This discrepancy is measured by the KL divergence, which is defined by the following equation. Basically, Ek of x defines the probability of class x at device k, and Q of x is the global probability of class x. The weight at device k is then defined by multiplying the scale divergence score by the ratio of the number of samples at device k to the total number of samples at all devices. This weighting scheme is designed mainly to avoid learning divergence. For the sake of time, I cannot dig more in the design of FeGAN, yet I encourage you to check the paper for more details about how we handle heterogeneous devices and server crashes. You can also find few details about our implementation of FeGAN. Now let's move to the last part of this presentation, in which I present to you the results of our evaluation of FeGAN. Most importantly, we test the scalability of FeGAN with respect to the number of contributing devices. We compare FeGAN to another variant of GAN distribution, namely MD-GAN, which relied on the parameter server architecture to distribute GAN training. On the x-axis, we have the number of devices we test with, and on the y-axis, we measure throughput given in the number of training epochs that the system can do per second. We can see here that FeGAN scales very well with increasing the number of devices, where MD-GAN fails to do so. The main reason for that is the choice for federated learning on which FeGAN relies and which scales very well to even thousands of devices. For the time limit, I cannot present more results here, yet in the paper we show that FeGAN tolerates GAN issues while saving bandwidth and converging faster than its competitors. This brings me to the conclusion of this presentation, which presented to you our new system, FeGAN. FeGAN distributes GAN training following the Federated Learning scheme. It scales better than its competitors while tolerating GAN-specific problems and skewness of data. Our code is public and fortunately evaluated and functional. I encourage you to check it out and use it. With this, I'd like to conclude my presentation. Thank you for watching.